In this section, we look at regular languages, but to answer some elementary questions about regular languages. That is, asked a question about any regular language, can we simply say yes or no to the question dealing with regular languages? We know the standard representations of regular languages being a automata, DFA, NFA, regular expression, or using regular grammars. So the elementary question can be answered in any one of the standard formats: DFA, NFA, regular expressions, or regular grammars. But many times we can even see that the question could be answered easily in terms of a DFA or an NFA. So for example, given a regular language, given the language in any of the standard representation, the elementary question could be, give me an answer in terms of a yes or a no. So, but we also need to give the procedure, how we arrive at the particular answer as a yes or a no. So describe the logic or the technique or the procedure behind answering the elementary question. Few examples. Let's say, given a regular language and a string W, does the string belong to L? This is often referred to as a membership question in a set. Does any given string W belong to the set of the language L defined as a regular language? Answer is, we know that there is a DFA that accepts L. Check if W is accepted by the corresponding DFA. That is, draw the DFA, see if there is a path from the initial state to the final state in the DFA for the W. So if there is a path that exists, W belongs to L. If there is no path from the initial state to the final state on the W, W does not belong to L. Another question could be, given a regular language L, how can we check if the language is empty? That is, take the DFA that accepts the L and then check if there's any path from the initial state to the final state. That is, there's no path from the initial state to the final state implies that the language is empty, null. By the way, it does not imply lambda. Lambda means, remember, in this case, language L would be contains an empty string lambda. So we're not talking about empty string, we're talking about empty set. So initial state is not a final state and there's no path from any initial state to the final state, then the language is empty. Another question, given a regular language L, how can we check if L is finite? That is, does it have a finite number of strings in the language or an infinite number of strings? For example, if I say L1 is a language that contains strings of length only 2, that is, I can say A, B, A, and B, or the alphabet A, B. Or if I define a language L2 as all strings starting with an A, then I have to say A, B, 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 and so on. So L1 is a language which is finite because it has been defined in terms of a fixed number of strings belonging to the language L1. Because we said L1 is a language which contains only strings of length 2. So it is finite. Whereas if I say L2 starting with an A, then it's an infinite number of strings. So given a property, we know that both of them are regular. So how do you find out if a language L, given language L, is finite or infinite? Sometimes it could be given as a regular expression, so it's not easy to look at the set and say it is finite. So the answer should be construct a DFA for the language L. Check if there is a walk with a cycle. This is the underlying aspect. That is a loop from the initial state to the final state. That is, if there is no loop, implies that there is a strict path from the initial state to the final state. So we can construct all the strings which has a path from the initial state to the final state. So this is finite. But if there's a loop involved, then it's infinite, right? Because this string is in the language, this string going around the loop once in the language, and I can do it any number of times is in the language. So the loop in any particular aspect of the DFA, there's a path in that particular walk from the initial state to the final state where there's a loop, implies that's infinite. We will expand on this property a little bit more little later on, but on the look of it, from the path from the initial state to the final state, if there's a loop, implies it's an infinite language. If there's no loop, implies it is a finite language. Another question that comes up often is, given two regular languages L1 and L2, are the two regular languages equal? Equal in terms of the number of strings that they accept. Remember, L1 and L2 could be infinite, so they can contain infinite number of strings. So visual checking of strings may not be possible. So the process is, the logic should be, find out if L1 intersection L2 bar union of L1 bar intersection of L2 is empty. So let's say why this should be true, and then we'll come back to the procedure. Because if L1 is contained in L2, then L1 is a proper subset of L2. Similarly, if L2 is contained in L1, then L2 is a proper subset of L1. In both cases, L1 intersection L2 bar is empty, and L1 bar intersection L2 is empty. So if both properties are true, that means L1 and L2 are exactly the same, proper, overlap each other in terms of the language L1, L2. So there are no strings in L2 that are not in L1, and there are no strings in L1 that are not in L2. So for example, take a finite set of strings in language L1 and finite set of strings in language L2. Let's say L1 is AA, L2 is AA, and AB. L1 bar would be an infinite set, all strings that are not in L1. So B, AB, BA, BB, and so on. All strings that are not in L2, L2 bar, L2 complement will be B, BA, BB, and so on. So what the intersection of L1 intersection of L2 bar would be? There's nothing in common, so it's empty, because L1 is a proper subset of L2, because all the strings in L1 are part of L2. but L2 intersection L1 bar is not empty because it contains at least L2 intersection L1 bar would be commonality would be at least be AB and many just AB for now. So it's not empty. So L2 is not a proper subset of L1. So both have to be empty for that to be the two languages to be equal. So if both of them are empty, L1 intersection L2 bar and L1 bar intersection of L2 is empty, then the two languages are equal. Otherwise, by the way, if L1 and L2 have at least one string that are not in common, then obviously L1 is not a subset of L2 or L2 is a subset of L1, and definitely L1 is not equal to L2. So the procedure would be to check if L1 intersection L2 bar union L1 bar intersection L2 is empty. So knowing L1 and L2, construct DFAs for L1 and L2, and then we can construct L2 bar DFA for L2 bar, and we can construct a DFA for L1 intersection L2 bar. Similarly, we can construct a DFA for L1 bar, complement of L1, intersection of complement of L1 and L2, and then we can construct a DFA for this. So there's a series of steps that we go through to construct a DFA for this. And we already shown earlier how to check if a DFA accepts an empty string or if the empty set. That is, if there's no path from the initial state to the final state of this DFA, then the two languages are equal. So language equality requires a little bit of a step process in terms of constructing many DFAs and then finding if there's a path from the initial state to the final state. And if there's no path, that means this language, the DFA that you construct is only empty set. That means L1 is equal to L2. Another question is, given a language L, does it contain any string such that the string W and WR are both in the language L? That is, does this language contain any one string which is a palindromic string? So where W and WR are both in L. By the way, this is not saying that the language is palindromic, which is all the strings have to be palindromic in this language. We're only saying that is there at least, the question is, any one string that is palindromic that belongs to the language L. So our procedure would be construct a DFA as before for the language L. We know how to construct the DFA for LR, the reverse of the language. And then we can construct a DFA for L intersection LR, right? And then check if the language above, the DFA is an empty set. That is there any one string which is acceptable by the DFA constructed for L intersection LR? If the language is not empty, that means that not empty, the string W and WR are both in the language L. So this is a process by which we can construct an algorithm of DFAs to show that it is answerable to find out if W and WR are both in L. So the questions seem to be simple enough, and the number of steps that you need to write down are not intricate because they depend only on the standard properties of the languages. So as a homework, I gave you some exercises at the end of this section to write down the series of the procedures to show that this question is answerable in a yes or a no format.